As we've discussed translations and dilations, we've covered what happens to the graph of the absolute value function as it's manipulated by the 4 basic arithmetic operations. With one catch. We've only been using positive numbers in our transformations. So, what happens when we start using negative numbers as well? For translations, this isn't a big deal at all. If we add a negative number instead of a positive number, that's the same as subtracting a positive number, which we've already covered. The same thing applies to subtracting a negative, which is the same as adding a positive. However, when we start multiplying and dividing by negative numbers, that's when something new is going to happen. So let's explore those circumstances and learn about the resulting transformation, a reflection. Before we try to take on the burden of understanding what happens when we multiply or divide by any negative number, let's remember that all negative numbers can be thought of as a positive number times -1. So really, we just need to figure out what happens when we multiply by -1. And if we take a look at our parent function, there are really only 2 places where we can multiply by -1. Inside the absolute value bars and outside the bars. So let's take a look at these 2 child functions and see what's special about them. First, we have the absolute value of -x. We'll start though, as we often do, by taking a brief moment to make a table for the parent function and graph it. We'll also use our normal color coding as we do this. From there, we can go back to f of x and proceed with our extended table of values for that function, being sure to place our 7 key values in the column immediately before we take the absolute value. And as is often the case, figuring out the outputs is relatively easy compared to figuring out the inputs. Notice, however, that as we go from the input column to the column of key values, we're multiplying by -1. So when we go the opposite direction, we just need to do the opposite of multiplication and divide by -1. But interestingly enough, dividing by -1 is the same as multiplying by -1. So we can actually keep this operation as multiplication by -1. Then, as we multiply each key value, we get our key inputs. As we graph our key points, you might notice something strange. This graph looks almost exactly like our parent function. There is a small difference though, and to highlight that difference, we need to regraph the key points from our parent function since they got covered up. But in order to see them better, we'll put them as rings around the points from the main function. As we do this, we can see that the order of the key points is flipped around. Even though the 2 graphs look the same, the points in the parent graph underwent a horizontal reflection to obtain the child graph. Another way to express this is that the graph was mirrored across the y-axis, meaning that points from the right side of the axis moved to the left side, and points from the left side moved to the right side. And despite the lack of major differences between these 2 graphs, this concept of a horizontal reflection is still important because there will often be a major and visible difference when we do horizontal reflections for other types of functions. To see how reflections can make a major difference in the appearance of a function, let's look at the other main child function that we wanted to consider, the negative absolute value of x. For this function, the first step is to take the absolute value, which means that our key inputs can just be the key values. Filling in the rest of the table is then just a matter of evaluating, which makes it easier to find our key points and graph the function. And once we graph this function, it becomes immediately clear what's different about the graph. It's upside down. That's because the negative sign outside the absolute value bars resulted in a vertical reflection, which means that all the points of the parent function got mirrored across the x-axis. Now that we've covered the main two cases of reflections, let's take a quick look at what happens when we multiply or divide by other negative numbers. First, let's consider the absolute value of x divided by -3, and give a moment to write out the extended table of values and make the graph. Now that the graph is done, we can see that the parent function was stretched horizontally, which makes sense based on what we've learned about dilations. We can also see that the graph was reflected horizontally, which makes sense considering we were dividing by a negative number. One last item of note about this function: while we could think of dividing by -3 as a single transformation that reflects and dilates at the same time, we can also just as easily break those transformations apart, both in our heads and in the way we write the function. If we simply think of the -3 as -1 times 3, then we can move the -1 around however we want, since dividing by -1 is the same as multiplying by -1. Thus, we could rewrite the function in multiple ways, and in our heads, we could think of this either as a reflection followed by a dilation, or as a dilation followed by a reflection. And now, for one more basic example, let's consider this function. Similar to the last one, we can split the negation and the multiplication apart in our heads and reorder those operations how we want. This means that we can think of this as a vertical reflection followed by a vertical stretch, or as a vertical stretch followed by a vertical reflection. Also notice that a couple of our key points didn't quite fit on our graph, but we were still able to approximately plot them off the edge of the graph. Normally, we would change the scale of our axes in this situation, but since it was close to fitting, we left them as is for this problem. Based on what we've learned about translations, dilations, and reflections, we should be ready to graph a wide variety of absolute value functions. So let's graph a few additional functions to solidify our skills. As you can see, this function has a bit more complexity than we might be used to, but the same process of filling in our key values and completing the extended table still works. Once we're done with that, we can graph the key points to see the shape of the function. You might notice something strange about this though. Inside the absolute value bars, we had a +3, which usually indicates a translation 3 units to the left. However, our graph moved 3 units to the right. We also had a -4 outside the absolute value bars, but our graph moved down by 8 units. So why was that? It turns out that if you really want the numbers in your function to directly correlate with the shape and location of the resulting graph, your function needs to be in this format. And if your function is in this format, then A will tell you the vertical scale factor, B will tell you the horizontal scale factor, and H and K will tell you exactly where the vertex of the graph will be. So let's put our original function into this format. First, we can distribute the 2 to both terms inside the parentheses to get this rewritten function. Then, we can factor out a -1 inside the absolute value bars to rewrite things this way. And since multiplying by -1 is the same as dividing by -1, we can finish off by rewriting the function this way. From here, you can see the -3 and the -8, which correspond with the graph moving right 3 and down by 8. You can also see that the graph was stretched vertically by a scale factor of 2. And if you look at the colors of the key points, you might notice that the graph was also reflected horizontally due to the division by -1. Now, if putting functions into this format is helpful to you, then by all means do that. It's a great way to see the relationship between a function and its graph. However, rewriting a function this way can also have its challenges. So if you'd rather find the key points using the original format of the function, or use another strategy altogether, that's great too. Each strategy can teach you its own lesson about functions and how they operate. Moving along, let's take a look at this function next. This time, however, we're going to adjust our function to be in the transformation format right away. So let's start by looking outside the absolute value bars at the division by -2. Notice in the transformation format that we don't have any division outside the absolute value bars. Instead, we're multiplying by a. So, how can we change our division by -2 into multiplication? Well, it comes down to reciprocals. The reciprocal of -2 is -1/2, which means that dividing by -2 is the same as multiplying by -1/2. This allows us to rewrite the function this way. But notice now that we need to distribute the -1/2 so that the k value isn't inside parentheses. So let's do that distribution, which gets us this new expression. Now it's time to look inside the absolute value bars and see how that compares with the transformation format. The only issue there is that we want to have division on the inside. But right now, we have multiplication. But thankfully, the reciprocal property works going from multiplication to division as well. If we're multiplying by 3, that's the same as dividing by 1/3, which allows us to make our final rewrite and achieve this function. Notice that we also wrote the +6 as -6, which will help us later when determining h. Now, instead of jumping straight into an extended table of values, let's see if we can make our graph based on the properties of the transformation format. We'll start by graphing the parent function, and then we'll take our horizontal scale factor into account. Recall that b is the horizontal scale factor, which turns out to be 1/3 for our function. So we'll graph our next step by compressing the graph horizontally with a scale factor of 1/3. Next, let's look at our vertical scale factor, a, which is -1/2 in our function. This means that we have to compress our graph halfway towards the x-axis and flip it over the x-axis, which looks like this. And finally, recall that h and k tell us the vertex of the graph, so we'll finish by shifting our graph to this location. From here, we could be done, but let's make our extended table of values quickly to verify our graph. And notice that we labeled our columns according to the original format of the function. This way, if we made any errors when converting from the original format to the transformation format, we should spot the difference in the graphs. Then, once we have our table done and our key points plotted, we can see that our graph is correct. Finally, let's take a look at a function that contains two sets of absolute value bars. While we can still easily make an extended table of values, the concept of key values and key points breaks down a bit here. Normally, we would place our key values in the column right before we take the absolute value. But since we're taking the absolute value twice, which column should we put the key values in? Well, it turns out that if we go with the second option, things will get messy when we try to work our way backwards. So let's go with the first option instead and fill out the table accordingly. Then, when we get around to graphing, we might look at these 7 points and think that the graph looks like this. However, if we evaluate the function for a few more inputs, we'll see that the graph doesn't look like this at all. In fact, it actually looks like this. The main point here is that the strategies we've been discussing about key points and the transformation format only apply when we have one core function involved, such as the absolute value, without any repetition. If we have more than one core function, or have a repeated core function, such as in this example, we'll have to try other strategies when graphing. The main strategy we could use when graphing a function like this is basically what we've done so far, to make a really long table of values. Eventually, after we've plugged in enough values, we can be pretty confident that the patterns we're observing will hold and that we can extend the graph further based on those patterns. However, just for a bit of fun, let's look at another strategy for graphing this function. First, let's look at the innermost absolute value and notice that the -5 is going to shift the parent graph 5 units to the right. Next, the -3 brings the graph down 3 units. At this point, we take the absolute value again, and since the absolute value at its core just turns negative numbers into positive numbers, we're going to take the portion of the graph that's below the x-axis and flip it so that it's above the x-axis instead. Next, we have to deal with the negative sign at the very front of this function. That negative sign is going to flip the whole graph over the x-axis, which will result in this. Finally, we have the +7, which will move everything up by 7 and give us our final graph. That concludes this video on graphing absolute value functions with reflections. Hope you learned something new, and thanks for watching.